Hi there, this is Shrewd Socrates. Welcome to today's video where we will be talking about a brief history of the power rule. So if you are taking calculus right now, one of the first things that you learn when dealing with the derivative, when computing derivatives, is the power rule. So let's take a look at the power rule as we know it. The derivative of x to any power k is k times x to the k minus 1, where actually the power k has to be a rational number. So if you're taking calculus, your teacher may have told you that this rule is still valid even if k is an irrational number. We will get to that in the next video. But for now, I want to discuss with you how we get to this power rule, and we will do it in levels, or if you would like, cases. So the basic case is when k, the power, is just a positive integer, like 2, 3, 4, 5, and so on. So our function is x to the power n, where n is a positive integer. And to find the formula for the derivative, we will use the definition of the derivative for any function f of x, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. So since our function is x to the power n, we want x plus h to the power n minus x to the n all over h. So I hope nobody is thinking that, oh, isn't that just x to the n plus h to the n? No, no, no. That is not how you expand a power of a binomial. You need Pascal's triangle. So this is something that we see usually in a pre-calculus course. And to make Pascal's triangle, notice that on the sides of the triangle, you have in yellow just the number 1. Okay? So yeah, this is like a honeycomb pattern. We have hexagons tiling our plane and creating these bigger and bigger triangles. So to form the third row, we take the numbers in the last row and we add them together. So 1 plus 1, we get the number 2 in between the two ones. Okay? So for the fourth row, we can now add 1 and 2 to make 3, 2 and 1 to make 3, and we have the 1 and the 1 on the left and the right, and so on. So for the fourth row, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and we have the 1 over there. So you can add as many rows as you want. If you want a sixth row, you have 6, 15, 20, 15, and 6 sandwiched by the 1s. Okay? So as we can see, Pascal's triangle is symmetric. Okay? So we have 4 reflected here on the other side as well. 5 reflected with 5, and 10 reflected with 10. Okay? So how do you use Pascal's triangle to expand a power? Let's do it for the fourth power over here, let's say. So we have x plus h raised to the power 4. That will mean we will have terms with coefficients 1, 4, 6, 4, and 1. Okay? What about x and h? So the first term will just be x to the power 4. The next term will be 4x cubed times h. And then we will have a 6. So plus 6x squared. And now h is also squared. Okay? So the powers of x are decreasing while the powers of h are increasing. What's next? We have 4x to the power 1 and then h to the power 3. Okay? And finally, we have just 1 h to the power 4. Okay? So that is how we expand x plus h to the power 4. And we can do that in general. So we have x plus h to the power n. You have x to the n, but the next coefficient is just n. Okay, so we saw that over here with the 4 based on the power 4. And you can also see it in Pascal's triangle. So let's scoot down over here and we see that, yeah, we go 2, 3, 4, 5, and so on. Okay? So after x to n times x to the n minus 1 times h, we will have something times x to the power n minus 2 times h squared, and so on. So it's the same pattern with the powers, okay? The power of x is going down as we move to the right, while the powers of h are going up, okay? So what do we do next? Well, we need to subtract x to the n to make the derivative, which is showing up again down here. So that simply cancels the first term, the x to the n over there. And then we have to divide by h, okay? So there's a power of h here, but h squared, h cubed, and so on, until h to the power n. All of those terms contain an h. So when we divide each and every term by h, that times h completely disappears, the h squared becomes only h, and the powers of h go down by 1, okay? So the penultimate term will have h to the n minus 2. The last term will have h to the power n minus 1. And that is very important because we're going to take a limit. So this is what is left of our difference quotient. So as h goes to 0, all of these terms are going to go to 0 because they each have an h factor in them, except for this term, the very first term. There is no h in that term. So the limit is simply the first term, which is n times x to the n minus 1. That is, of course, the power rule that almost all of us begin with, okay? So let's apply it to x to the 7. We will, of course, just get 7 times x raised to the power 6. Okay, so next, what happens when k is a negative integer? Okay, so we can write it as k equals the negative of n, where n happens to be a positive integer. Okay, so we will write it as x to the minus n, and we can rewrite that as the reciprocal 1 over x to the power n, where this time n is positive. Okay, so that's important because we can now apply the reciprocal rule for derivatives, which is almost always proven in a basic calculus class. So the derivative of the reciprocal of a differentiable function is a fraction. It is the negative of the derivative of that function divided by the square of that function. Now, most of you probably know the reciprocal rule as a special case of the quotient rule. Something like low d high minus high d low, square the bottom, away we go. Okay, so in this case, our g of x is x to the n, not 1 over x to the n, but just x to the n, because that is what we see here in the reciprocal. Okay, so according to the reciprocal rule, the derivative of 1 over g of x is negative g prime over g of x squared. So I wrote that over there, and let's carry out the computation. So according to what we have, g of x is x to the n. We know the derivative of g of x because we proved the power rule when n is a positive integer. So we have, let me copy this down here, we will have negative n x to the power n minus 1. Okay? And then g of x squared will be x to the n quantity squared. Okay? So I hope you remember your rules for exponents. If you have x to the n squared, what do we do with the powers? We multiply them together. So we get n times 2, or better yet, 2 times n. So let's copy this over here. We have x to the power 2 times n. Let's erase that. All right. So what do we have now? We have a fraction, but there are 2 x's. Okay. Well, we know that we can also apply the other rules for exponents. If you have a quotient, you simply subtract the powers. Okay. So what do we do? Well, let's do it in the numerator. So we have the numerator, and we will subtract from the exponent of the numerator, the exponent of the denominator, which is 2n. So we will have n minus 1 minus 2n, but we can simplify that. N minus 2n is simply the negative of n. So we can, whoops, not over there, but over there. So we have negative n x to the power minus n minus 1. Okay, however, what did we say? Our function is x to the minus n. Our k is minus n. Okay, so do we see k in this formula? Minus n, that is k. Minus n, that's also k. So we can rewrite this as k times x raised to the power n minus 1. All right, so that is, k minus 1, because our exponent, our k is negative n. Okay, so that is the power rule when k is a negative integer. Okay, so this time, if we have 1 over x to the 7, we did x to the positive 7, now we have x to the negative 7. So our k is negative 7, we have dropped the power, negative 7, x to the power, subtract 1 from negative 7, minus 7 minus 1, we get minus 8. If you were thinking minus 6, sorry, it's minus 8. We can stop right there, or if you like, we can express this as a fraction. This will be negative of 7 divided by x to the power 8. Okay, so depending on your teacher, maybe this is the preferred answer, or both would be acceptable answers. Okay, we are now at the third level, or the third case. What happens when k is a full-blown rational number? Okay, so k is a fraction, p over q, where p and q are integers, and q is not 0. We can also impose that p and q are in lowest form. They have no common factor. So our function is x to the power p over q. We are going to use implicit differentiation. Okay, so that means that we will write our function as a symbol y, a variable y. So y will be x to the power p over q. We will look for dy by dx. Okay, we can't do it directly because we don't have a formula for the derivative of x to the p over q. That's what we're looking for. Okay, so what we're going to do is we're going to do some algebra first, so that we get to a point where we can apply derivative formulas that we know. And advance warning, when you take a derivative of any expression involving y, you must apply the chain rule. And that is where the dy by dx pops out. Okay? So, what is the algebra that we have to do? Well, we have y is x to the power p over q. Okay, so let's copy that down here. Y equals x to the p over q. Okay, so we don't know how to take the derivative when the exponent is a fraction, so let's turn it into an integer. We don't like the over q here, so if we raise both sides of this equation to the power q, that will get rid of the q. Okay, so y to the q will be x to the power p over q, and then we will raise that expression to the power q. Okay, so we reminded you of the exponent rule. When you have two exponents here, one inside the other, we multiply the exponents together. Okay, and that's exactly why we do what we did, because that gets rid of the q. Okay, so p over q multiplied by q, you're left with just p. Okay, so the great thing now is that both exponents, q and p, are integers. So we can apply the power rule when the power is an integer, because we have a legitimate formula whether q or p is a positive integer or a negative integer. Okay, so we're going to take the derivative of both sides, the derivative of y to the power q on the left, And on the right, we want the derivative of x to the power p. Okay, so we can apply the power rules now, which say that you get q times y to the power q minus 1. But remember, every time you take a derivative that has a y in it, you have to apply the chain rule. So we have to multiply by dy by dx. Okay. On the right side, we don't have a y, so we simply have p times x to the power p minus 1 by the ordinary power rule. Okay, great. So we can now solve for dy by dx, isolate it. Dy by dx is, you have this on the right side, which we will divide by what appears on the left side beside dy by dx, which is this. All right, awesome. But wait a minute, this has both x and y in it. So we can get rid of the y because y is just x to the power p over q. Okay, so let us do the replacement. Replace y with x to the power p over q. Okay, so that is wonderful. And oh, guess what? We have p over q here, and that is good because p over q is our exponent, k. Right? So we can separate that out, p over q. And then what do we have left? We have x to the p minus 1 and x to the p over q raised to the q minus 1. And once again, we can apply our power rule. When you have two powers like this, you can you can multiply the exponents. Okay, so we have, let's move over to the next line. Okay, so this multiplying the two fractions, the two exponents together, p over q times q will simply give you p. So let me erase that. And we will just get p for the first term, but you also have p over q times negative 1. So that's minus p over q. Okay, so let's review. P over q times q is just p, but p over q times negative 1 is just minus p over q. Okay? Oh, and check it out. We have p in both the numerator and the denominator in the exponents. So we will apply the same strategy as before. We are going to subtract the powers, and we'll do it in the numerator. So p minus 1 minus the quantity p minus p over q. Okay, so get into the habit of putting parentheses whenever you are subtracting a complicated expression from another. Okay, some of the worst mistakes, common mistakes you can make is forgetting the parentheses and you just get minus p minus p. Nope, that is not how it works. So what do we get? The p's will cancel, but you have minus minus plus p over q, and we still have minus 1. Okay, so I believe we are at the final step. When we subtract the p's are going to cancel. And then we are left with positive p over q. So that goes better at the front of the exponent. Oh, check it out. We have p over q, x to the p over q minus 1. So p over q, that's our k, and we have x to the power k minus 1. That is the power rule when the exponent is a fraction p over q. Okay, so we can apply that now to two examples. We have a positive fraction here and a negative fraction down here. Okay, so let me hide that for a second. So let us apply our power rules. So drop the exponent, which is just 7 over 4, and then subtract 1. 7 over 4 minus 1, so that's 7 minus 4 is 3, x to the power 3 over 4. Okay, did you get the same answer? Similarly, okay, let me give you a second or two to do this, or you can just pause the video. How about that? Pause. Okay, we're back. So, drop the exponent, negative 5 over 3, and then subtract 1. Okay, so this time you have a minus 5 over 3, minus 5 minus 3, you get minus 8 divided by 3. Okay, and again, you can leave that answer as it is, or you can rewrite it with a positive exponent. So the minus 8 over 3 becomes positive 8 over 3 if you put the x in the denominator. Okay, so we get minus 5 over 3, x to the power positive 8 over 3 in the denominator. All right, excellent. So coming real soon, we don't know why this rule is still true if k is any real number. Okay, so what if you had x to the square root of 2? What does that even mean? So we are going to see that in our next video when we talk about the natural logarithm function. And we will see exactly, okay, now can we have some kind of meaning to the expression x to the power square root of 2. All right, so that's our video for today. Short one for a change. So thank you so much for watching, and I hope you enjoy the rest of your day.